Alright, so this video will explain the fundamental theorem of calculus, and I'll begin by trying to motivate the theorem a little bit and give some insight into why it might be true. So we'll start with a very simple velocity function, 2t plus 3. And let's say we're trying to figure out the question, find the displacement from time equals, let's say 1 to time equals 4. Right, now we know displacement is change in position. Well, another way to say it would be your final position minus your starting position. Right? If you know where you end up and you know where you started, the difference would tell you how much your position changed. Well, we've learned in class that if I have velocity and I take an integral of velocity, or an antiderivative with respect to time, then what I get is the position function. So I get x of t equals t squared plus 3t plus some c. We don't have any information to solve for c, so we'll just go with that. And now, final position. Okay, well, that would be the position we're at when time equals 4. So let's plug that in. And then let's figure out what's happening at time equals 1. And so plugging that in, we get 4 squared plus 3 times 4 plus c minus, and then plugging in 1 squared plus 3 times 1 plus c. Right away we can see that the plus c's are going to cancel out, right? We're going to distribute this negative. So those are just going to go away. We're left with 16 plus 12 minus 1 plus 3, and that's going to be 28 minus 4 is 24. So that is the amount that the particle moved, if we're talking about a particle moving back and forth on a number line, from its original position. We don't know where it was, okay, but at time equals 1, it was over here. And it may have moved back and forth. Of course, this is a simple velocity function. It only moved to the right. But it could be that it moved back and forth or whatever. This number is simply telling us the distance between where we began and where we ended. Okay, so we want a total of 24 units from where we started. Let's come at this another way now. All right, let's look at the velocity function. Okay, we all know what 2t plus 3 looks like. It's just some linear function going up like this. This is v of t. All right, and let's look from the interval from 1 to 4. All right, well, if we consider this region, what we end up getting is a trapezoid, right? If you turn your head to the side, you can see these are the two parallel bases. And we know the formula for the area of a trapezoid, right, is height times base 1 plus base 2, all over 2. So our bases, let's see, so we would want to figure out the height of this line, but we have a function, right? So that's simply v of 1, which would be 5, and v of 4, right? 2 times 4 plus 3 is 11. Okay, so we would say the height of this thing is 3, right, from here to here. The bases are 5 and 11 divided by 2. And so if we calculate the area of this trapezoid, we also get 24. That's not a coincidence that those are the same number. Okay, we've been talking about this idea that area under a velocity function gives us displacement. Well, now we also know how to find displacement using the antiderivative. And so what the fundamental theorem is going to do for us is connect these ideas. This is just some motivation, and of course we will be doing some examples with position, velocity, acceleration, but in general now, we can say the following. This is the fundamental theorem of calculus. Let little f be a function that is continuous on an interval from a to b. No asymptotes, no gaps, nothing weird happening. As long as that's true, then the integral from a to b, that's how we say that symbol, of little f is equal to big F of b minus big F of a, where f is the antiderivative. or big F rather, is the antiderivative of little f. Okay, this symbol here, this is called a definite integral. I apologize if you can hear Charm chewing on her chew toy in the background. Definite integral means find area under the function from a to b. That is what that symbol tells you to do. It is as simple, I say that lightly, as taking the antiderivative. Think what we did back here, right? The antiderivative of velocity. We plugged in our endpoints and we took the difference. And it ended up being that area. And this is going to be useful. What if our velocity function is like t cubed or something? And we want to find the area from 1 to 3 or something. Well, that's not going to be a nice shape, right? There's this curve here. And what the fundamental theorem will let us do is it will let us find that area exactly. We don't have to approximate with rectangles anymore. So let me show you a few examples. Okay, if we wanted to find the area under 3x squared plus 4 from 3 to 5, which I've represented over here with a picture. You don't need to draw a picture for these. It just kind of helps you visualize what's happening. Right? The fundamental theorem tells me to find the area from 3 to 5, okay, which is what this definite integral says. What I want to do is first I want to find my antiderivative. Okay, well, here it's easy enough to do, right? We know the antiderivative of 3x squared is going to be x cubed, and the antiderivative of 4 is going to be 4x. So this is an easy formula. Of course, it's not always so easy to find an antiderivative, okay? And that can be the issue. But for these, it's not so bad. And then what we want to do is we want to plug in our bounds, right? Our upper bound and our lower bound, our end point and our starting point. And so the symbol we use is this, okay? We put a little bracket at the end. And what that says is the following: plug in 5 into the formula you just got, the antiderivative. Plug in 3 and subtract. Okay, this is doing the f of b minus f of a part of the theorem. You found your antiderivative, now you plug in your bounds. You can certainly use a calculator to do this. I'm going to do it by hand here, but you can power through this arithmetic in whatever way you see fit. So this is going to be, let's see, 145 minus 39, and so if it was 40, so this is going to be 106. What you have found is this area. And you're not approximating it. Okay, you're not estimating what it is. You have found the area exactly. You win. And if this seems a little too simple, this is a very nice, elegant theorem. It seems like it should be a lot harder to find that area, and yet, as long as we know what the antiderivative is, it's just a little bit of arithmetic and we're there. Okay, of course, that's the thing. It's not always so easy to find that antiderivative. But this is the fundamental theorem of calculus at work. All right, and just a few more examples. Okay, if we do 4x cubed minus 2, okay, again, we start by taking the antiderivative. You may want to pause the video and try these yourself, by the way. Okay, so taking the antiderivative is x to the 4th minus 2x. And we evaluate over the bounds, okay, which means we're going to plug in 3. I recommend parentheses for all this so you don't forget to distribute and things like that. Oops, sorry, 2 times 2. All right, and then you want to simplify that out. So 81 minus 6 minus, let's see, 16 minus 4, so that's going to be 75 minus 12, okay, which is going to be 63. And you win. That is the area under the curve. Sine, let's see. So we're going to integrate. The integral of sine is negative cosine, or the antiderivative of sine, from 0 to 2 pi. Plug that in. Okay, so we'll do negative cosine of 2 pi minus, careful, double negative here, negative cosine of 0. But wait a minute, I get negative 1 minus negative 1, but that just equals 0. It's kind of strange. You might want to think about that for a moment. You might want to try to figure out that yourself before I go ahead and explain this. The other thing you might be wondering at this point is, what happened to the plus c? Hey, Mr. Tyler, you said every time I take an antiderivative, there's a plus c. And there is, you're right. But think about what happened here when we got that plus c. They ended up just canceling out, right? You're going to do plus c minus plus c, so that's just going to go away. So had I written a plus c back here, think about what would have happened. It just would have gone away, even if I had put it there. So when we're doing a definite integral, you don't need to put the plus c. You could. It wouldn't be wrong if you did. Over here, if you put a plus c here, you would certainly get the right answer, but you're just kind of doing a little bit of extra work that you don't have to do. So when you are doing a definite integral, and again, that's when there are bounds, you don't need the plus c. If you are doing just a regular old, indefinite integral, like we were doing last week, then you do need the plus c, because now nothing's canceling out. Okay, you still got to put it here, but when you're plugging in the bounds like this, the plus c is just going to cancel out anyway. So what about this 0? Okay, so let's think about the graph of sine for a minute. Remember that area under a velocity curve gives displacement, right? It gives the amount of change. So let's think about sine as being a velocity function. Now think about what would happen. First of all, your velocity is 0. Okay, if we start at 0. And then the velocity gets positive, right, as we go this way. So your particle is going to start to move to the right. And it's going to speed up. And then it's going to start to slow down. So it's going to go to the right, go to the right, go to the right. Then the velocity is 0 again. Think about what happens now, right? The velocity becomes negative, which we know means the particle is going to start traveling to the left. It's going to speed up in this direction now. And it's going to speed up and speed up and speed up until we get to here, and then it's going to start to slow down. And think about it, you get as much positive velocity as you do negative velocity. So you're going to end up back in the same place. You started here, you ended here. Your displacement is 0. Even though you traveled forward and traveled backwards, you ended up in the same place. So your end position minus your start position is 0. You didn't go anywhere. So how can this make sense now with area? Okay, what we want to do is we want to treat area below the x-axis as being negative. Okay, so when you are integrating, when you are doing this definite integral, what that really means is find area between the function and the x-axis. Now, when we're above the x-axis, it's going to look like this. When we're below the x-axis, right, between the x-axis and the function, it's going to look like this. Okay, so what we do is we allow area, I put that in quotes, right, because we learn in geometry area can never be negative. Okay, but in a calculus context, it makes sense to allow that area under the curve to be considered as negative accumulation. You move forward 2 units. If you calculated this integral, you would find this is 2. And then you move backwards 2 units. And so altogether, you don't end up going anywhere. So that's a little strange. Okay, you'll get used to that though. Area below the x-axis is considered negative because it represents moving to the left as opposed to moving to the right. You'll get used to that. A few more things here. These are just some properties of the definite integral that you need to know. Occasionally these are useful. If you try to integrate from a number to itself, if you go from a to a, so if you integrate from 2 to 2, Well, you can think about what would happen. I mean, graphically, we're taking a function and we're not going anywhere. So what's the area of a line, right? That's just 0. The other way to think about it is do the fundamental theorem. What would you do? You would take the antiderivative, you would plug in 2, and then you would plug in 2, and you would take the difference. But anything minus itself is just going to be 0. So that one's kind of obvious if you think about it long enough. All right, one that's a little less obvious is what happens if you switch the bounds. A to B, B to A. Okay, as a picture, right, if we're going from, let's see, A to B, like this. Now, if this is velocity, right, this is displacement. Well, think about it. If you're integrating this way, this should be positive, right? The particle's moving to the right, so the displacement should be a positive number. It should be moving right. But if you integrate backwards, what you're doing is you're sort of reversing time. You are playing the tape in reverse. You are playing time backwards. And so what happens now is you would be starting here and thinking about where were you at the beginning. You would be losing position. So it ends up being the opposite. That's a little hard to imagine. So let me just go right to the fundamental theorem to help justify this. Think about if you were going to do this integral. With the fundamental theorem, you would do f of a minus f of b. Right? You always plug in the top number first. If you were going to do this integral, you would do f of b minus f of a. Well, these are going to be the same number, but opposite. Okay, so we need that negative sign. That's where that's coming in. Think about it. If you do 7 minus 5, or you do 5 minus 7, if you switch the order, you get the same answer, but opposite signs. Okay, so if you switch the bounds of an integral, it becomes the opposite of what it used to be. The last property is if you split up an integral. And where would this come up? This would generally come up with like a piecewise sort of function. Okay, imagine you have some like quadratic and some, let me just make up a linear function. I'm just making stuff up, okay? I don't know if those would intersect or whatever, but let's pretend you had two formulas, okay? If you're going to integrate, you have to take an antiderivative. But this is going to be a little tricky because you have two different functions that you would be taking the antiderivative of. So to make life easier, let's just say we were trying to integrate from here to here. What we would do is we would break this up. We would break it up where one function turns into the other. And if we call this a, c, and b, okay, what we're doing is we're going to first integrate from a to c. We'll take this area. Then we'll integrate from c to b. So we'll take this area. But you can see if you just add whatever you get here plus whatever you get here, it's going to be as if you had just integrated over the whole interval. So that summation just gives you the whole thing. Okay, so this is just showing that that geometric intuition you have still works, right? If you had a shape like this in geometry, how did you take the area? You probably broke this into like 2 rectangles. Okay, and your teacher said as long as you know the parts, you can add them up to get the whole. Well, that still works for integration. So where the derivative was a lot of algebraic intuition, the integral is going to be a lot of geometric intuition. Okay, this is the more geometric part of this course. And to finish up this lesson, let me bring in some geometry. So I meant to put some numbers on this thing. Let me do that now. We'll say 4, and 6, and 8, 12, and -2. Not drawn to scale. Okay, this is time and this is velocity. So here's a question that I have seen on the UConn test. I've seen things on the AP test that are like this. They tell you the position of the particle at time 0, okay, is 0. And they want you to fill in the table. So we can start by filling in. We know the position at 0. The question is, where is it at time 4? Okay, well, one way to answer that question would be to think about, we could find the displacement because the displacement would tell us the change in position. Now, we don't have any formulas or anything, but we do have a picture. And so if this is lining up with 4, which I meant it to, these are supposed to be straight lines, by the way. Think about, if you found this area, that's easy to do. That's just a rectangle. So this area is 24, right? 6 times 4. Well, again, area under the curve is displacement. And so what that means for the particle, wherever we started, right, is 0 in this case, over the course of these 4 seconds, think about it. The velocity is a constant 6 units per, let's just say, second. So if you move a constant 6 units per second for 4 seconds, you're going to end up 24 units from where you started. All right, well then what happens? All right, where are we going to be at 6? Well, now we have a triangle. So let's calculate the area of this triangle. And of course we know how to do that. 1/2 base times height. The base is 2. The height is 6. So that's going to come out to 6. Think about what's happening. The particle had a constant velocity of 6, and now it starts to slow down. It's still moving to the right, right? The velocity is still positive until we get to time equals 6 when it's going to stop. But it's still moving to the right. And so what happens is, yeah, it slows down, but it goes an additional 6 units over to 30. Okay, so a lot of students will say that the answer is 6 here. Careful. It's not telling us where we are. It's telling us how far we went from where we were. It's telling us how much motion we did. So we were at 24 at 4 seconds, and then between 4 and 6, we got 6. That means we went an additional 6 units to the right. Now we continue. What's going to happen at 8? Now be careful. We started to go below the axis here. Take this area, 1/2. Base is 2. Height, this was meant to line up with 2, sorry, is 2. Let's just pretend it does. Now you can think of it this 2 ways. Geometrically, this is 2 times 2, or if you just go with the numbers, the height of this rectangle is -2 in this case, because it's going down. Either way, you end up getting 2, but because it's below the axis, we want to consider that as -2. And again, if you're not convinced, think about the velocity becomes negative at this point. So the particle should be moving backwards now to the left. And so we're going to go 2 units backwards. We're going to end up at 28. One more part here. Let's get to 12. So by this is 28. One more part. Okay, we take this rectangle or triangle rather, 1/2. Base is 4. Height is 2. That gives us 4, but below the axis. So we're going to call that -4, and we end up back at 24. Okay, -4 representing motion to the left because the velocity is negative. So we end up back at 24. Okay, the particle moved to the right, it slowed down, it stopped, it moved to the left, it sped up, it slowed down, and it stopped again at 24. We're going to continue with this on Wednesday. I hope this taught you most of the concepts. You should go try the homework now. Ignore the question about average value. We'll do that on Wednesday. And if you have any questions, send me an email. Thanks, everybody. Have a great day.